Welcome to SH Lectures. The topic of today's discussion is carbohydrates, and the chemistry of carbohydrates will be discussing into consecutive 5 sessions, session 6, 7, 8, 9 and 10, where we will be discussing about the chemistry of the carbohydrates. So in today's lecture, let us just look into the definition and classification of carbohydrates. So what are carbohydrates? Carbohydrates are polyhydroxyaldehydes and ketones are substances that yield such compounds on hydrolysis. Majority of the carbohydrates have general formula of CH2ON, but some also contain nitrogen, phosphorus or sulfur. The most abundant monosaccharide in nature is D-glucose, which is also known as dextrose. A common disaccharide, which is stable sugar, sucrose, contains 6 carbon sugars of D-glucose and D-fructose. Common polysaccharides include cellulose, starches, and many other components. So this is the overview of the classification of the carbohydrates, depending upon the uh, uh, hydrolysis process. We have monosaccharides, we have oligosaccharides, and we have polysaccharides. Monosaccharides are those classes of sugars which cannot be further hydrolyzed. They are monomers, single units of sugars. They are being further classified into on the basis of the functional group. Uh, on the basis of the functional groups, they can be either aldoses or they can be ketoses. Aldoses are they contain an aldehyde group, and ketoses they contain an ketonic group. Uh, Depending upon the number of the sugars and carbon atoms present, they can be 3 carbon containing, 4 carbon containing, 5 carbon containing. 3 carbon containing are called as trioses, tetroses, pentoses, hexoses and heptoses. Now let us come to oligosaccharides. Oligosaccharides are nothing but oligo means few. They contain few monomers of sugars connected together by a glycosidic linkage. They can be disaccharides, they can be trisaccharides, and they can be tetrasaccharides. Disaccharides are maltose, lactose, and sucrose. Trisaccharides, an example for trisaccharide is raffinose. Tetrasaccharides, stachyose. Similarly, we have polysaccharides, which are nothing but the polymers of sugars. So here, majority of the monomers are linked together by glycosidic linkage to form large polymers. These polymers can be of two types: homopolysaccharides and heteropolysaccharides. Homopolysaccharides examples are starch, dextrin, glycogen, cellulose, inulin. All these are examples of homopolysaccharides. Heteropolysaccharides, here the sugars are not same. In homopolysaccharides, we have same units of sugar connected together by glycosidic linkages. Here the sugars are different. They contain different components like heteropolysaccharides. Examples are hyaluronic acid, heparin, chondroitin sulfate, dermatan sulfate, and keratan sulfate. So apart from the carbohydrate component, some other component is present. Hence they are called as heteropolysaccharides. So now let us move on to some of the properties of monosaccharides. Monosaccharides are colorless crystalline solids that are very soluble in water but insoluble in non-polar or organic solvents. Most are sweet in taste. The backbones of monosaccharides are unbranched carbon chains in which all the carbons are linked by single bond, and they can be in open chain form. One of the carbon atom is double bonded to an oxygen atom to form a carbonyl group. If the carbonyl group is at any other position, a ketone group, the monosaccharide is a ketone. So if there is an aldehyde group present, we call it as an aldonic sugar or a aldose. If it has a ketonic group, we call it as a ketose sugar. Monosaccharides with 3, 4, 5, 6 and 7 carbons in their backbones are called as trioses, tetroses, pentoses and heptoses. And many of the carbon atoms to which to which hydroxyl groups are attached are called as chiral centers. Uh, Chiral centers. They give rise to many stereo isomers found in the monosaccharides. Yeah, these are the representative monosaccharides. So this is a glyceraldehyde, and yeah, this is a glyceraldehyde, which is a, you can see three carbon, carbon 1, carbon 2 and carbon 3, and this is a dihydroxyacetone, which is also a 3 carbon compound, and we have here glucose, which is 1 2 3 4 5 6 carbon compound, and we also have fructose, which is also a 6 carbon compound, and we have ribose, and we also have pentose. So these are 5 carbon sugars, and these are 6 carbon sugars. These are 3 carbon sugars. uh, all of the monosaccharides except dihydroxyacetone contain one or more asymmetric chiral carbon atom, and thus it is possible to have lot of isomers. They are optically active. We can have D and L isomers because of the chiral carbon. They can also be stereomers that are not mirror images. They are called as diastereomers. Thus, of the 16 possible aldohexoses, 8 are D forms and 8 are L forms. Uh, the reason D form predominates in nature is unknown. So D form of sugars are abundantly present in the nature when compared to the L forms of the sugars. So these are again the same structures. These are D and L forms. So this is D form, and this is the L form. This is the D form, and this is the L form of glyceraldehyde. So here you have an D-glucose and D-fructose, D-glyceraldehyde and L-glyceraldehyde. We can see both are mirror images. The OH group is present on the in one in D form it is present on the right side, in the L form it is present on the left side. So both are mirror images. So similarly, we have a phenomena called as epimerization. So if this is a molecule of glucose, we can see there is a formation of epimers. So glucose and galactose are called as the epimers of mannose, and galactose are called as the epimers of glucose. When we compare glucose with mannose, we can see an formation of epimer at C2 position, and here in galactose it is at C4 position. And these are the structure of aldoses: 3 carbon, 4 carbon, similarly 5 carbon and 6 carbon. So and this is similarly the structure of ketoses. The only difference between aldoses and ketoses is the presence of the functional group. In aldoses we have CHO group, and in ketone we have C double bond O. We have this ketonic group. Yeah, and the formation of the two cyclic forms of the D-glucose, and this phenomena we call it as an mutarotation. In aqueous solutions, monosaccharides with 5 or more carbon occurs as they form into an cyclic structures. So it forms open chain structure. It forms a cyclic structure. Uh, See here we can see the open chain structure of glucose, and it gets converted into an ring structure. Uh, the anomeric This is due to the anomeric carbon atom, the new chiral center created when the sugar ring is formed, and we can expect again two isomers. Uh, yeah, I'm sorry. We can expect two isomers. That is, yeah, we can expect two isomers. They are uh, the alpha D glucopyranose and beta D glucopyranose. So here in alpha we have H, C and OH, and in beta we have OH, C and H. The OH is present. The position of the OH is going to change. Two anomers are produced, alpha and beta. So this is the comparison of Fischer projection of glucose and alpha D, ring structure and Fischer projection, and we call this ring structure as Haworth projection, and this open chain structure we call it as an Fischer projection. And these are the ring structure of some of the common sugars. Alpha D glucopyranose, beta D glucopyranose, alpha D glucofructofuranose, and beta D fructofuranose. And this is all about all the overview of all the structures what we have seen. So properties of monosaccharides. Uh, Simple monosaccharides are reducing agents because of their ability to reduce potential oxidizing agents like Cu2 plus to Cu plus and hydrogen peroxide. They are thus called as reducing sugars. This reaction forms the basis for Benedict's test for qualitative analysis of simple sugars. Glucose, the blood sugar, and an immediate source of energy for cellular respiration. So with this, we'll stop here on the monosaccharides. We'll continue with disaccharides.